Okay, welcome to note set 19. For some reason I tried this just a minute ago, got part way, and it stopped recording on me, so we'll start over. We're talking about note set 19, section 4.2, and we're talking about projections, which is a big idea in a lot of areas of electrical and computer engineering, and in particular in something called least squares. Which you've probably heard about fitting a least squares line to a set of data, but it's much bigger than that. So let's motivate the idea here. So suppose we've got some vector b, and so here's that vector b, and we've got a z-axis. So this is the z-axis here. Even though I don't have it labeled, it's clear as we go x, y, z. And we're going to imagine shining a light from far away. So if we're projecting down onto the XY axis, we're going to imagine a light's way up there, infinitely far away. And so the shadow would be directly underneath this. And that would actually form a right angle between the light ray from the tip of B down to the plane. And likewise, if we imagined shining a light over this way, we would form a right angle there. And so what we're really thinking about, if you think about it, if I were to pick any other vector here, the distance between that vector and B would be longer than the one that's directly underneath. So we're really trying to find the closest vector in the plane or line that we're projecting onto. So another interpretation is that we're trying to find the part of vector B that lies in that plane or lies along that line. And so that's what we're striving to do here. So let's ask another question. If we are comfortable with that view, we might ask, are there matrices that produce these projections? So I take a matrix, I multiply it by B, and it gives me P1. I get another matrix, I multiply it by B, and it gives me P2. And we're just motivating this here with this simple case where we're projecting onto the XY plane or the Z-axis, but we'll see soon that we can project onto any subspace that we want. So there is actually a matrix, and we'll call it P for projection. And each matrix will give us a different type of projection, or vice versa. For each projection that we want, we'll have a different matrix. So we've got our vector B, we've got some matrix P, and it gives us little p as the vector that's created. Now, suppose that we talk about P1, matrix P1, being the matrix that when I multiply P1 times B, it gives me the projection onto the z-axis. So there's that vector out to that point right there. Now suppose so now I can write that like that. Now suppose I imagine taking that vector, P1, which is right there, so there's little p1, and I project that. So I'm projecting P1 onto the z-axis. Where does it go? Well, it doesn't go anywhere. It stays right there. So we can say that P1 times B gives us the same as P1 times B. And so if we look at these two things, we can see that P1 squared must be equal to P. And in fact, you can take that to any integer. So P raised to any integer power, if P is a projection matrix, will be just equal to P. So it's a very special matrix. It's not just any kind of matrix. So it's, for that alone is kind of interesting. What matrix times itself is equal to itself. So what do these specific projection matrices look like for this particular case, where we're projecting our vector, some vector B, given here, onto the z-axis? What does that projection matrix look like? And what does it look like when we're projecting onto the xy plane? Well, if we call the projection onto the z-axis P1, call the projection onto the xy axis P2, There's our B. We know that P1 has to be equal to this, right? It's sitting right here, so its XY components are 0, and its Z component is equal to the Z component of P, because we're shining this light and it just goes perfectly horizontally over to P1. So we set the 2, 3 equal to 0, and we keep the 4. So there's our projection. And likewise, this would be projected down. Its Z component of the projection is 0, but the X and Y components are the same as for B. So we keep the 2, 3, and we zero out the third element. So the projection matrices are pretty easy to see for this case. So to project onto the Z-axis, now, I'm simplifying things here. We've got zeros all the way out here. I just didn't fill them in. But the key is on the diagonal. We've got zeros for the components that are going to get zeroed out, and we've got a 1 for the component that's going to be kept. So that's the projection onto the Z. Projection onto the XY plane, pretty easy to pick out too. We need to keep 2 and 3, but zero out 4. So we keep 2 and 3, and we zero out the third element. And again, obviously there's zeros out here as well. So for that case, it's pretty easy to look at the scenario and figure out what the projection matrix needs to be. But suppose I have some plane that goes through the origin but is tilted. It's not the XY plane, it's some tilted plane, and I want to project B onto that. It's harder to even visualize what the result should be, and it's even harder, there we go, I was expecting that. It's even harder to visualize what the projection matrix will look like. But that's what we're trying to figure out. You give me a characterization of some subspace, some hyperplane, or if we're in 3 dimensions, some actual plane. And I'd like to figure out, given a description of the subspace, how do I figure out the projection matrix that will project any given vector in the full space down onto that given subspace? That's what we're after. So let's just illustrate this here before we go on to that general case. We can easily see that these things do exactly what we're saying that they do. Some other observations that we can see. For this case, the projection onto the z-axis, P1, and the projection onto the xy plane, those projections themselves end up being perpendicular to each other. And there's a reason for that. The main reason is that the xy plane and the z-axis are orthogonal complements of each other. So if we project B down onto the xy plane, then we project it onto the z-axis. Since the z-axis is orthogonal to the xy plane, obviously the projections are going to be orthogonal to each other. And from that, we can also see that for this case, and we'll see some generalizations of this idea, for this case, if we take our z projection and our xy projection and we add them together, well, it's easy to see that we get back B. And we can capture that idea by saying that the two matrices, the two projection matrices added together must give us I. Because if we multiply both sides by B, over on the left side, we're going to get P1 times B gives us P1. Capital P2 times B gives us little p2. So this is just another way of writing that. And then if we just swing this P1 over on the other side, once we find P1, we can find the projection onto its orthogonal complement by just subtracting the projection, the given projection, from the identity matrix. So this little step right here is kind of a key idea that allows us to, once we know a projection onto one subspace, to find the projection onto the orthogonal complement of that original space. You just take I minus the original projection matrix. So our goal in general is you tell me the column space. You give me the column space of some m by n matrix. or equivalently, the subspace spanned by n being less than m. So we've got n linearly independent vectors where n is less than m in Rm. So that's going to be some strict subspace of the full Rm. Let's start this off with projection onto a line. So there our subspace is just one-dimensional and some line. So suppose you've given me some vector that defines a line. So as soon as you give me that vector, I know that that vector spans this one-dimensional subspace. That's the line of interest. So we have one vector in Rm. N is equal to 1 in this case. So here's a picture, and I'm just doing this in R2. I could do it in R3, but here's our vector A, and we can think about the line extending forever in both directions. Let me get rid of that here. And I'd like to find the projection of some given B down onto that line, and we'll call that projection P. So there's the vector P. And again, I'm showing that this vertical line here that goes from the tip of B down to the projection is orthogonal to A. And that really is the key. What we're trying to find is another way to talk about projections is to find the closest vector on the line defined by A, the vector that's closest to the given vector B. And it's pretty clear that if I pick any other vector, the line between them will be a little bit longer than this vertical line here. I say vertical relative to A. This orthogonal line, orthogonal to A. So, you know, if you're sitting at the tip of B and you want to get to the line defined by A as fast as possible, you would move directly towards that line so that your motion is perpendicular to the line A. I think that's pretty clear. So that's what we want, the closest point. So since this vector A is the span of everything on that line, P is just going to be some multiple of A. So we hypothesize some number x hat. So our job is, given B, given A, figure out the number x hat that I have to multiply A by to get this point here. Okay, so we use that x hat as the thing that we need to find first. Once we find it, we just multiply that by A, and it gives us the vector P. So if we look at this one-dimensional case, sometimes we're interested in that, but we're really more interested in a general higher dimensional case. But this will give us a hint as to how this thing's really going to work and what it's going to look like. So here's the picture again. The dotted line here between B and P we'll call E to kind of represent error. It's the error between B and the projection P. And since P is going to be equal to this vector, which is some number x hat times A, to scale this thing back to here, we can write E as B minus x hat A. Remember, we know B, we know A. X hat is the thing that we're trying to find. So we can work with this to try to derive what's the right form for x hat given B and given A. This is how math works. So we know that E is perpendicular to A. So we can take the inner product between A and E, and we know that that must be equal to 0. We know that because we know that the error vector must be perpendicular to A to give us the closest spot. Okay, so that's what we've got to work with, but we know that we can write E in terms of two things that we know and one thing that we don't know. And then we can take that and inner product with A. So this equation involves two things that we know, A and B, and it involves the one thing, x hat, that we don't know. So then we can just solve that equation for x hat to figure out what it needs to be. That's amazing. So we know that we can plug in for E here. And now we just manipulate this. We multiply the A transpose through both of those terms. And we get something that looks like that. Oh, we're so close to being able to solve for x hat. If we solve for this, we swing this thing over to the other side. And then we say, aha, this thing must be greater than 0. How do we know that? Well, A can't be a 0 vector because why would we want to be projecting B down onto the 0 vector? That would be projecting B onto the origin. Well, anything projected onto the origin is going to be 0. So we know that we're picking A to be something that has non-zero length, and A transpose A is nothing more than the length of A. So we know that is non-zero, and so once we get this thing over to the other side, we can isolate x hat by dividing it back to the other side, and we get A transpose B on the top, and we get A transpose A on the bottom. Remarkable. Maybe not that remarkable, but it is actually. It's pretty cool. So let's look at this a little bit more. What we're doing here in the top part is we're saying the projection involves the inner product between B and A. And even better, if we think about A being normalized by that, what we're doing really is an inner product between B and the unit vector that lies along A. So if we think of that as the unit vector, we're trying to come up with a number x hat. And we take that unit vector, which is this whole quantity, it's being normalized by its length, and do an inner product of it with B. That's a pretty key idea. So if you can get that burned into your brain, that would be great. Now what we're going to do, we now have a form for x hat. So we can plug that in up here. And what we're going to do, just to have things turn out a little bit nicer in our final result, is this is just a scalar, right? We can check that, right? A transpose B, that's an inner product, so that's a scalar. In the denominator, it's A transpose A, that's the norm of A, that's a scalar. Scalar over scalar is a scalar, so x hat is a scalar, so I can actually move it to the other side. So I'm going to write it there. It'll just make things turn out a little bit nicer so that we can compare it to the more general case. So there's what we've got. We've got A times x hat. And here's what we've got for x hat that we've stuck in on the right-hand side, just because it'll be nicer. Now let's look at two special cases. Special case number 1. What if B is equal to A? So in other words, B is lying perfectly along A. What would P be? Well, P is just equal to B, which happens to be A. So the projection of B onto itself, x hat is equal to 1. Okay, that's pretty simple. If B is perpendicular to A, so now in that case, B is actually sticking off this way. And remember, I'm shining a light that comes down perpendicular to the line A, so the shadow of this would be right there. It's like standing out in the sun at high noon. The sun is directly over your head. You see just a dot of a shadow down at your feet. That's it. No extension of your shadow. So those are two special cases. Just keep in your mind. So what's the projection matrix that we're talking about? We figured out how to get P by finding x hat, multiplying it from the right onto A. So here's our x hat. Well, remember, P is the thing, the projection matrix is the thing that multiplies B. So right there is B. So let's pull that out and group everything else together. And I claim that's a matrix, and we'll call that matrix P. It's the projection matrix onto the line A. So sometimes you use a subscript on this projection matrix to indicate what you're projecting onto. So maybe we would say P sub A. So there's our projection matrix. Why is that a matrix? Well, look at the bottom. The bottom is just a norm. It's the length of A, so that's a scalar. But what about at the top? See, at the bottom I got A transpose A, gives me a scalar. At the top, well, and let me back up, and the bottom is a so-called inner product. The top is a so-called outer product. It's a column times A transpose, a row. Column times a row gives you a matrix. And when that column and row are the same vector, in the same dimension, you get a square matrix. So P is a square matrix, and I claim that that is the projection matrix, and that's pretty interesting. So anytime you've got a column times a row, you're going to get a matrix, but it's actually got an interesting characteristic to it. So we're projecting onto a line. We should think that the rank of P should be 1 if we think about like range space. The range space, or the column space of P, where we can end up, is dimension of 1. So the rank of P has got to be 1. And so we actually have this interesting result, which we can show another way, that anytime you have a column vector times a row vector, you get a matrix, and the rank of that matrix is always 1. And let's just see why that is. So let's take our column vector V times a row vector, which has, we're showing the elements, A1, A2, and so on. Now, if we use our properties of multiplication, we can pass this V through. And since the A's are scalars, we can put them in front. So our first column of the resulting matrix is some number times V. The second column is some other number times V. In fact, every column is just some multiple of V, and so all of the columns are linearly dependent on each other. So there's only one linearly independent column, and that is the definition of the rank. So we've just proved here that any column vector times any row vector gives us a matrix of rank 1. And that makes sense. We know that our projection matrix should have a column space of dimension 1, so it should have rank of 1. See how all these ideas just keep tying together. It's not just a scattered amount of, a scattered bag full of unrelated ideas. These things just keep coming back in a consistent kind of way, connecting back to each other. So that's kind of the good part, and it's also kind of the bad part of this kind of course. But really think about it as the good part. You learn a few things, and you can use those to understand. Well, you learn a few things early, and you'll be able to use those to understand new things later. So everything builds on everything else. All right, let's go to the more general case. We figured out how to project onto a line given by one vector, line which is the span of a single vector. Now let's start off with n vectors, a1 through an, and we're specifically saying that they are vectors in some space Rm, m-dimensional real space, and we're going to explicitly say that n is less than m, so that these things span strictly some subspace of Rm. There's not enough of them to span Rm, but we are going to insist that these things are independent. Now, if they weren't independent, be no big deal. We would just throw away the ones that were dependent and leave ourselves with the independent ones. We would be spanning exactly the same subspace, so we wouldn't even miss those that we threw away. So there's no harm in assuming that if you've given me a bunch of vectors, I've already kind of thinned them out to just the independent ones. Or, even better, you realize before you give me these that there's no point in giving me anything that other than a set of independent vectors, and so you pre-thin them and then give them to me. Now here's our problem. I want to find the combination P, which is just a weighted combination of these vectors with some scalars out in front of each one, so just a linear combination, such that the resulting vector P is the closest vector in that subspace to vector B. Right? We're doing a linear combination of these vectors that span our subspace. So we know that P is going to be inside this subspace, and we'd like to find the closest one. That's the idea of a projection onto a subspace. Find the closest vector in the subspace. So here's a picture. That blue rectangle is evoking the idea of some subspace spanned by the vectors, and we're not showing the vectors, but A1 through AN, but presumably this is the origin. We could have, A1, A2, A3. Now, obviously, I'm showing you in three-dimensional space with a two-dimensional subspace, so technically I can't draw more than two independent vectors here, but in a higher dimensional space I could have more of them. But that's the basic idea. So the vectors A1 through AN span the space that's being evoked by this blue rectangle. And we're looking for the closest point in the plane. That's this vector P. Shine the light vertically, or perpendicularly rather, to the blue plane, and the shadow is right there, the closest point. And we know that this error vector E is therefore perpendicular or orthogonal to the entire plane. Now, when n is equal to 1, this is what we did for projection onto a line. Now we're doing this for higher dimensions, but this is consuming that earlier special case. Now, if these, I've already stated, if these vectors are not independent, then there are vectors in there that are not needed to span the subspace, and we can just get rid of those. So let's think about putting those vectors into the columns of some matrix A. So I've got matrix A, it holds the vectors, and so now this x hat is going to be a vector with the elements that are here, x1 hat through x hat 1, x hat n. Those are the elements of this result, this vector x hat. And we can see that this forms the linear combination. X hat 1 weights the first column of A, x hat 2 weights the second column of A, and so on and so on and so on. And the hat here, common terminology in math, symbology in math, we use hat often to represent kind of the best choice, the optimal choice. So x hat is the best one, the one that will make P closest to the plane. So here's the steps to compute the projection. And again, we're not really interested in numerically doing the computings. Yes, sometimes we are, but our real focus is, how does this work? Why does it work? What does it look like? How do we connect this? How do we understand this? So let's go through the steps, not for the purpose of coming up with some final formula that you can write on some formula sheet, take into an exam, and blindly apply. No, that's not engineering. What you want to do is understand why you have that formula. What does it tell you? What does it mean? So let's do that. Step 1, find the vector x hat. Okay, seems like a reasonable step. Step 2, find the projection, which we know is just, we take the vector x hat that we just found and we pre-multiply A times x hat, and that gives us the projection. And then step 3, interpret that to find out what the projection matrix looks like. And really step 4, I don't show it here, that's the big thing. Try to understand what it looks like, why it works that way, what it tells you. But the key to getting there is to understand the geometry, and we've said it already. The key is that the dotted line, this error vector, the B to P line here, that goes to the nearest point in x hat, and it's perpendicular to the subspace. So what does it mean to be perpendicular to a subspace? We've said this before. It means that it's orthogonal to every vector in the subspace. But since the columns of a matrix span the subspace, in fact, they're a basis for the subspace because they're linearly independent and they span, every vector in the space can be written as a linear combination of the A's. So each column of A itself must be perpendicular to E, and that's the key. So this error makes right angles with all the column vectors. So we can write out n equations. A1 is orthogonal to the error. all the way down to an is orthogonal to the error. So there's n equations. And if we group those together, we see this action of the individual vectors here will end up matching with the combined action of that matrix times the error vector. So that must give us equal to 0. Now, subtleness on the notation here. Could have done a better job on my part notating this, but these are all scalars, and this is actually a 0 vector. So I could have made that last 0 bold to illustrate that a little bit better. Okay, so what do we do now? Well, manipulate. Always a good thing to just try to play around and see where things will go. Pass the A transpose through, pass the A transpose through, swing it on over, and we end up with something that looks like this. And this is called the normal equation, or the normal equations, since we're talking about multiple variables here and multiple matrix form of multiple equations. Now, we can find x hat and p, little p, the projection itself, and big P, the projection matrix, by the 3 steps, starting from here. This has already established the criteria. This is the criteria. X hat is the solution to this set of equations. Now, we should really ask ourselves, is there a solution? We've looked at systems of equations like this, and we've seen square matrices, tall matrices, short matrices, in the column space, not in the column space, full rank, not full rank. We know all those scenarios, and sometimes there is a unique solution, sometimes there's no solution, and sometimes there's infinitely many solutions. How do we know that there is just one solution here? Well, we'll get there eventually. But for right now, we're just going to kind of take it as a given. So we're going to find the x hat and the p. Here's the 3 steps. So we know that a times x hat is the closest thing to b, and it comes from the normal equations. So that's the key right there. There's our normal equations. Let's solve them. So we will cover this, the details of this, but for right now we're just going to believe. We're going to believe. Well, it is actually pretty easy to see that A transpose A is a symmetric matrix, although we'll prove that later. It's not terribly difficult to prove it, and you might even be able to just look at that and say, yeah, I see it. Certainly it's n by n. We know that A itself is m by n, and so A transpose is n by m. A is m by n, so the product is going to be n by n. So hey, it's square. And so if it's invertible, we can invert it and solve for x hat. And that would be the case where there is a unique solution for x hat. So we will see this condition later. We're just stating it. It is invertible. So it being A transpose A. So A transpose A is invertible if the column vectors A that make it up are independent. So if we have that case, and I told you we had that case. In fact, I even said, if that isn't the case, throw out the ones that are dependent. You're still spanning the same subspace. So everything is good, as long as we can prove that statement later, which we will do. So, under the assumption now that that is true, if the columns of A are independent, then A transpose A is invertible. There's the inverse, which we create, multiply by the right side to break free x hat. There's our solution. We now have x hat. So now let's see how it works. So now, see why I put the x hat on the right in the line case? Because it has to be on the right here, because it's a vector that's forming a linear combination of the columns of A. So it's got to be on the right here. For the line case, it could be either way, and it seems more natural for scalars to put them out in front, but I forced you to put it to the right so that it would match up with this. So now we get the full form. So to get B, I just take, I have my A transpose B here, and I have to have the A transpose A inverse. That all gives me the X hat, which I then multiply into A. But we can also look at this way. So let me clear off some of this ink here just so we can see a little bit better. Instead of grouping it as the X hat stuff working with A, let's group it a little bit differently. Let's group all of this stuff together operating on B. Well, isn't that the definition of a projection matrix? Yes, it is. So what is our projection matrix? There it is. And we claim that that is an n by n projection matrix. And you can work out the dimensions of that. And you should also guess that the rank of this matrix P is, can you guess? Sadly, I can't hear anybody out there in video land saying it. I'm hoping you're saying it. It's got to be rank of n, because we're projecting onto an n-dimensional subspace. So we know that the column space of P has to be this n-dimensional subspace, and that's the definition of its rank. So we know that P is a rank n matrix. So it's an n by n rank n matrix. So that in and of itself tells us that that is interesting matrix that comes out of that. Wait a minute. I'm starting to doubt myself here. This is wrong. This is M by M. M by M projection matrix, and it has a rank of n. So it's not full rank, actually. We should know that. So I got a little misled there because I had indicated it incorrectly on the notes. I will try to fix that before I post the notes, but just keep in mind this is M by M. So it's an M by M matrix that does not have full rank, but has rank of n still. So that part was correct. Now let's compare this with what we saw for the line case. So here we can see that we've got the same kind of thing if we think of the little a playing the role of the big A. But notice that here we've got A transpose A down in the denominator. That's because that is a scalar, and inverting a scalar is just forming its reciprocal. Here we cannot put it down in the denominator because it's a matrix. There's no concept of dividing by a matrix. But there is multiplying by the inverse. And so that's why we have to do that. And then we can see a similar characterization here. And then finally we see that we get the rank 1 matrix here, and we get a rank n matrix there. So you can see it's not two different things. It's just the same idea, where this thing we're looking at now is the more general case that consumes the line case as a special example. All right, speaking of example, here is an example. So here's our matrix A. So these are the two columns that define the subspace. So we're in R3 as our full space. We've got two vectors that are spanning our subspace. It's pretty clear that they are linearly independent from each other. So we've got a two-dimensional plane in R3, and here's the matrix, or I'm sorry, the vector B that we want to project onto this. Find x hat, find little p, find big P. So pause the video here if you want. Don't look at your notes. Give it a shot, and then come back and see how we go through it. All right, hopefully you gave it a shot and got the right answer. Now we could just immediately write this down. We don't really have to write this down, but I wrote it down again to help you remember that that's where it all starts. This all boils back to, ties back, all boils down. Pick my cliche phrase. It all boils down and ties back to the orthogonality of the error to the columns of A. That's the key. And then we solve that and we get this. So there's our x hat. So we can form our A transpose A, and we see that we get something that looks like this. You should be able to do all those multiplications by hand. We look at that and see, 2 by 2 matrix with 2 linearly independent columns. So it is invertible, so we can form the inverse of that. We do A transpose times B, and we get that in 6, 0. And now, we could solve the normal equation. So we could solve it as a system of equations. So we could use any of the methods that we've been using to solve the system of equations. We could do row elimination and then back substitution and so forth. Any way you want to do it. Or you could try to compute the inverse of A transpose A, whichever one. And so step 2, we then take A times that result, and we get something that looks like that. Step 3 is our projection matrix. And to get that, we do kind of need to, at least from this point of view, we need to find that inverse, A transpose A inverse. And fortunately for a 2 by 2, we've seen a formula for that. It's pretty easy to do. So we use this formula. We get something that looks like that, and then form the whole thing. There's our projection matrix that looks like that. So that's a 3 by 3 matrix, and you can check that. Well, you could put it into MATLAB and use the rank command. You could also do, reduced row echelon form of this. Find how many pivots you got. How many pivots are you going to end up with? 2, because this better be rank 2. So you could do that too, because you know how to do all that stuff now. So we're seeing that this matrix A transpose A plays a key role in this, and we claimed that it was invertible. We claimed that as long as the columns of A were independent, that A transpose A was full rank and was invertible, therefore invertible. But let's see that. Well, first of all, let's caution you that you cannot split this. You can't say A transpose A total inverse and split it into A transpose inverse times A inverse. That doesn't work. And one thing you can do to kind of see what would happen if that were true, if you take this and plug that in for this, you'll quickly find that your projection matrix will, if that were true, your projection matrix would always be the identity matrix, which is no projection matrix at all, really. It's a projection onto the full space. So this certainly cannot be true. So don't make that mistake. So let's look at this A transpose A matrix a little bit further. So we've said that our matrix A will be rectangular, and that's because we're picking n columns in Rm with n strictly less than m. That makes it that we're strictly forcing ourselves to have some subspace in R sub m. So we're going to have fewer columns than we do rows. So not only is this matrix going to be rectangular, it's going to be a tall matrix. So we've seen tall matrices, square matrices, short matrices. That covers all the cases. And tall matrices show up a lot in engineering stuff. We'll soon get into least squares, and we'll see tall matrices show up there for a very specific reason. But all right, so we've got a rectangular matrix. Clearly, A cannot be inverted, and clearly A transpose cannot be inverted. So not only is this not true, but these things don't even exist. Okay, so we cannot do that. But what we do know is that A transpose A is going to be symmetric, and that's easy enough to see. Take A transpose A and take its transpose. Now, using properties of transpose, we're going to interchange. So we'll take that and move it over here and transpose it. We'll take this and move it onto the other side and transpose it. And then we have A transpose transpose is just equal to A. And so what do we have? What have we just established here? We have that A transpose is equal to itself without the transpose. That's the definition of a symmetric matrix. So it's symmetric. And we also know that A transpose A is square. That's pretty obvious. In fact, it has to be square to be symmetric. So we've essentially already shown that too. So it's square. It might actually have an inverse. Well, we've already alluded to the fact that it does, because that was in our solution right there. A transpose A inverse shows up as a part of our solution. And we claimed that it has an inverse exactly when the columns of A are independent. And we're going to prove that. That's the answer to this question, but when? It's when the columns of A are independent, and we're going to address that issue soon. We'll prove it and see. But to do that proof, it's handy to have an additional property that we can prove first and then use. So we'll take a look at that. So here's the property. A transpose A and A have the same null space. Now notice I didn't say anything about whether the columns of A are independent or not. This actually holds true regardless of what A is. So you take any A, you form A transpose A, it's going to have the same null space as the original A. Now that doesn't sound like a terribly useful thing, and maybe it isn't in and of itself, but it ends up being useful to prove what we really want to show, which is that A transpose A is invertible exactly when we have the columns of A being linearly independent. So let's prove this first. All right, so we're talking about the null space. So let X be in the null space of A. Then we know that for that X, AX is equal to 0. Okay, let's multiply both sides of that by A transpose, multiply from the left. And so now we're going to have A transpose times that gives us A transpose AX. We're going to have A transpose times 0. Well, anything times that 0 vector is going to give us 0, because all that's going to do is take 0 times every column in A transpose, add them all together, and what do you get? 0. So now we have that. Whoop, went too far. And so what does that tell us? It tells us that X is also in the null space of A transpose A. That's what this says, right? If I take X and multiply it times this matrix, I get 0. So X does that for A, X does that for A transpose A. So X is in the null space. And so what we've shown is that if X is in this null space, it's in this null space. Now we need to check the other way, because it could be that the null space of this one is actually bigger than A. So it could be, if we don't check, that there are some X's here that are in the null space of that, but are not in the null space of that. So we better check. We just checked the other way. So let's check this way. Now let X be in the null space of A transpose A. Then we have this. Now we cannot make any progress by multiplying by A or A transpose like we did above. That doesn't help us. But we do a similar trick. Now we're going to multiply both sides by X transpose. And so now we get something that looks like this. So that thing on the left is equal to 0. Now we look at this carefully and we say, well, I can pull the transpose from each of those and transpose one product. What would it be? Remember, we have to switch them around, switch their order around. So we can rewrite that as AX transpose, that's this first bit, times AX, that's the second bit. Now, I haven't done anything different, I've just rewritten this, so it's still equal to 0. But now look at this. Oh, I notice I just missed something here. This is a vector transpose times itself. That's the norm. Well, technically the norm squared, so I should have a square here. That's the norm squared of AX. So the norm squared of AX equal to 0. Remember, we said the only thing that has 0 norm is the 0 vector. Therefore, since this thing has 0 norm, AX must be the 0 vector. So there we have it. So X is in the null space of A transpose A, and x is also in the null space of A. So we've now shown both ways that if it's in the null space of one, it's in the null space of the other. That means they have exactly the same null space. Now we're going to use that result to very easily prove that A transpose A is invertible if and only if, so we got to go both ways, if and only if A has linearly independent columns. So proof. We know that A transpose A is square. We've already established that. So we can use the fact that a square matrix is invertible if and only if its null space is 0. Well, how did we get that? Well, we know a square matrix is invertible if and only if its rank is full. So, and its rank is full precisely when its column space is the entire space. That means its null space is going to be just the 0 vector. So see, all these things, they keep coming back and being reused. It's all interwoven. So we know that. So all we really need to do is kind of riff on this idea. Square matrix is invertible if and only if its null space is just the 0 vector. So let's do the if part. If A has independent columns. So, all right, let A have independent columns. Then we know that the null space of A must only be the 0 vector. That's what it means to have independent columns. That the only x that I can multiply from the right and end up with 0 is all elements of x being equal to 0. So the null space is just the 0 vector. And from the above, meaning this, so from the above meaning this result that we have up here, since A and A transpose have the same null space, A has a null space of just the 0 vector, A transpose A must have the null space of just the 0 vector, and a square matrix is invertible if and only if its null space is the 0 vector, therefore A transpose is invertible. So we did the if part. If A has independent columns, then A transpose A is invertible. Let's do the only if part, because really this if and only if, that's what this is saying. So here's the only if part. It has to go the other way. Let A transpose A be invertible. Now we must show that if that is true, then A must have independent columns. So let's check it out. Since A transpose A is invertible, from our above discussion, we know that it must have a null space that's only the 0 vector. And from the above, this result up here, we know that A transpose A and A have the same null space. So the null space of A is 0, and the only way that a rectangular matrix A can have a null space that is 0 is if its columns are independent. And there we have it. We've proved that. So remember, we started off saying, you give me n linearly independent columns that span some n-dimensional space, subspace in Rm, and I can find the projection matrix onto that subspace. Now that projection matrix needed this result because the projection matrix has A transpose A inverse in it. But we've now guaranteed that if we start off with linearly independent columns, and there's no reason why we can't, because if you try to throw in a couple dependent columns in there, they're not giving me any other part of a different subspace. So I throw them out. So I can always do this. So you give me some set of vectors, I find the span of that, keep the bare essence, the linearly independent parts that span that. So in other words, a basis, I take that basis, form a matrix with those basis vectors as the columns, I can now find the projection matrix onto that subspace. Amazing. So here is the problem setup that we were just describing there at the end. Given n independent vectors in Rm with n less than m, find the combination that's closest. If they're not independent, then we can throw away the ones that are dependent. We don't need those to span the subspace. That means that A transpose A is guaranteed to be invertible, and we can form this projection matrix just fine. Thank you very much. Just like that. And that's the end of this set of notes. We will be using these ideas in the next set of notes for doing least squares. So take a look at this, get it down. And again, it's not about being able to numerically compute these things. It's about understanding how it works, why it works, and what you can do with it. I'll see you next time.